One evening in early September 1859, the aurora borealis could be seen across America. It was blood red and so bright that miners emerging from their tunnels in the Rockies thought that the dawn was breaking. So bright, in fact, that newspapers could be read even at midnight. It wasn't just in America. These aurora were seen around the world. No one knew what had caused them. But earlier that same day, in a leafy garden in the home counties, a gentleman astronomer had noticed what he called a white light flare on the sun's surface. Back then, the flare and the aurora were two apparently unrelated astronomical curiosities. But we now know that that flare, a coronal mass ejection, was the cause of that spectacular aurora. And when this violent phenomena occurs again, it could cause devastation to our modern technological world. Welcome to the sky at night.
The sun, the most familiar thing in the sky, the source of heat and light for all of life here on Earth. It's unimaginably vast, accounting for 99% of the solar system's mass. This near-perfect sphere is 1.4 million kilometers in diameter, created by the fusion of hydrogen and helium that's burnt for the last 5 billion years. Astronomically speaking, though, it's nothing particularly special. A G-type main sequence star, a common yellow dwarf. But appearances can be deceptive. Its surface rages with solar flares and eruptions of plasma, particles and radiation that travel far into space. This activity we call the solar wind. But particularly violent eruptions are called solar storms. And none is more dangerous than a coronal mass ejection, or CME, because these have the potential to bring our modern, technological society to its knees, turning the sun into our very own Death Star. Tonight, we'll find out just how bad the impact of a CME could be, and what astronomers are doing to monitor our local star in an attempt to forecast when they might happen. But first, Maggie steps back in time to 1859.
In Victorian Britain, solar astronomy was an acceptable gentleman's pursuit. And one gentleman did it particularly well. Richard Christopher Carrington. Unfortunately, we have no idea what he looked like because there are no known portraits. But here at the Royal Astronomical Society, we have these. Here's handwritten records of his sunspot observations. Small dark patches on the solar surface. And he was meticulous about keeping records of these transient phenomena. From his observations, Carrington made many important discoveries. He saw that different latitudes rotated at slightly different speeds, which meant the sun wasn't a solid body, but fluid. But he also noticed that sunspots could be the start of a solar storm. It says in here that on Thursday, September the 1st, 1859, the morning was clear and cloudless. And that meant Carrington was doing his usual, taking observations of sunspots. He was using his telescope to project an image onto a screen. But it's also got here that for a little while he stopped to cut down some trees. But then, at 11:18, he drew these. But these were no normal sunspots. Because then, two brilliant beads of blinding white light appeared in what Carrington describes as a kind of conflagration. But more mysteriously, 5 minutes later, they were gone. What Carrington had witnessed was a massive magnetic explosion. a coronal mass ejection, a huge cloud of charged particles thrown from the surface of the Sun. 18 hours later, an electromagnetic storm slammed into the Earth. It became known as the Carrington event. The main talking point at the time was the spectacular aurora, visible across the world. And although a few telegraph systems went a bit haywire due to power surges, the effect on everyday life was pretty minimal. But don't forget, this was 20 years before the light bulb was invented. That was back then. Today, things would be very different.
Coronal mass ejections aren't unusual, but they vary in size and in direction. So the question is, what are the odds of a Carrington-scale event striking the Earth today? And what effect would it have? At the University of Reading's Meteorology Department, I met Chris Scott, who's been studying space weather and the possible impact of CMEs for over 20 years. So when we talk about the solar wind and space weather, what is it that's actually happening at the Sun, on the Sun's surface?
Well, the Sun's a magnetic fluid, and as that magnetic fluid rotates, it causes the magnetic field to become twisted and distorted, and a twisted magnetic field is storing energy. And that can cause eruptions both in light, those are solar flares, and in material, these mass ejections that we talk about. And these eruptions are enormous, 1 billion tons of material, and travelling at 1 million miles an hour. And so we're interested in which direction these things are moving in, because of course if they come towards our Earth, they can impact the technologies that we rely on.
So these are these things called coronal mass ejections, these CMEs. So one of the reasons this is a big deal now is that we're surrounded by a fleet of satellites that we depend on. What's the impact of a CME if it hits our fleet of satellites?
Firstly, these charged particles can build up a static charge within the metal parts of the spacecraft, and then it can actually break through that insulation and cause electricity to flow in ways that you don't want. Other times you can have just single electrons that are accelerated through the electronics of these spacecraft, and because everything now is miniaturized onto circuit boards, it can cause all kinds of issues as it clatters through the circuitry. I mean, a satellite like Sputnik wouldn't have cared two hoots, it would be all valves and huge technology, but now that we're shrinking everything down, that's where these electronics get vulnerable.
And what about here on the ground? What effects does a CME have on the infrastructure here?
Well, it disturbs the Earth's magnetic field. That magnetic field therefore generates currents to flow in the atmosphere. If any of that charge leaks into the extended power grids that we have, they're not designed to take the sort of currents that we see. And so if you have a direct current flowing through a transformer, say, in a power grid, then it will cause...
Like in a power substation or something
Yeah,
like that.
yeah. It will cause the electronics to heat up, and that can cause the insulation to fail, which can cause the transformer to fail. So in the very biggest storms, we have seen transformers fail quite spectacularly.
That's actually happened because of solar weather.
Yeah, there's a very famous event in Quebec in 1989 where some power systems were disrupted for many hours in October, I think. So it's not a time you want to have no power in Canada.
Let's take a specific example. We've heard about the Carrington event in the 19th century. What would happen if that event happened now? How would it affect us?
If we think now, we have spacecraft we rely on for positioning with GPS, we have communication satellites, we have weather satellites, we have even the stock markets are connected by satellite in some way. But also we have extended power grids on the ground. We have lots of wireless technology which we don't know how that will respond.
How likely is it that something like the Carrington event could happen today?
Well, we know that the Sun is still capable of producing these events. There was an event in 2012 that luckily didn't come towards our planet, but it did go over one of the spacecraft that we have monitoring the solar wind, and it maxed out all the sensors on that spacecraft. So studying that, we think that was as powerful, if not perhaps more powerful than the Carrington event. So we know the Sun's still capable of producing these events. It's just that coincidence of a massive CME and one that heads towards Earth.
And that's just luck, essentially. We either get one or we don't.
Yes.
And how are we doing with forecasting? Can we say what the Sun will be doing next week, next month, next year?
With space weather, we're probably around where meteorology was in the 1950s. But the things that we find very tricky at the moment is understanding exactly when one of these active regions will undergo the reconfiguration that will release the material as a mass ejection.
So we see the magnetic fields winding up,
yeah,
but we don't know when they're going to snap.
No, that's such a chaotic process. Once a CME has been launched, we can start a forecasting process. So you can characterise how big it is, how fast it's moving, and more importantly, what direction it's going in.
Well, this all sounds very alarming. How worried are you about what a CME could do to our infrastructure?
The UK government have recognised that space weather is a problem. It's on the National Risk Register, and it's the same sort of level as a flu pandemic. So spacecraft manufacturers are looking to see what the extreme environments in space are so that they can manufacture them to withstand those to a certain tolerance, or they have redundancy in their systems. And the same goes for the power grids on the ground.
Chris, thank you very much. We'll come back and talk to you next time there's a CME on the way.
Please do.
Both NASA and ESA are about to launch satellites to get closer to the sun than ever before. We'll take a look at those later in the programme. But the need for predicting space weather with accuracy is already pressing. In 2014, the Met Office opened their Space Weather Operations Centre, one of only 3 places around the world to forecast the sun's disruptive effects on Earth around the clock. So we asked Elizabeth Rizzini, who presents our online stargazing weather forecast, to report on current solar activity.
So let's take a look at conditions today on our local star, and unsurprisingly there's some beautiful sunshine, and as ever surface temperatures are at a blistering 5,500 degrees Celsius, though the temperature on the sunspots can drop as low as 4,000 Celsius. Now, at the beginning of August, the solar wind speed was increasing slowly to around 330 kilometres per second. That's just under 1.2 million kilometres per hour, with a density of around 6 protons per cubic centimetre. Of course, the sun has got an 11-year cycle of activity in terms of solar radiation, sunspots and flares, and currently we're heading towards the solar minimum of the quietest solar cycles since the beginning of the 20th century. And so far over the last month, the sun has been almost completely spotless, with no further significant activity, sunspots nor CMEs expected on the Earth-facing side of the sun. So happily, not too much going on really at the moment, and in the long-term outlook, it's looking similar. So spacecraft, satellites, power supplies should be safe for the foreseeable future.
Trouble is, the foreseeable future in space weather forecasts is, at most, just a few days. There's still much about CMEs that we don't know, from their direction of travel to their size and shape, let alone being able to anticipate long-term just when they might occur. This is something that's being addressed by the STEREO experiment and a willing cohort of citizen scientists. Julia Wilkinson is one of them. So Julia, tell me about STEREO. What is it and where is it?
STEREO, or the Solar Terrestrial Relations Observatory, was launched by NASA in 2006, and its mission was to image the sun, and also the space between the sun and the Earth.
And that means it has to be in a special place to do that.
It does. In fact, NASA launched 2 spacecraft. One was placed in orbit slightly behind Earth.
So we've got Earth here.
Yeah, and the orbit of STEREO B, as it's called,
okay,
behind. And another was placed in an orbit slightly ahead of Earth, which is STEREO A. And as you can see, in 2011, they were in this position almost opposite each other. One of the advantages, obviously, of having 2 spacecraft is that they had a unique view of any Earth-directed storms because they could see from the side. And it can give us some quite spectacular images as well.
So what are we looking at here?
Here we can see the solar wind, which is all the stuff coming off the sun, because the sun leaks all the time. If you think of the sun as a leaky football, it's leaking all the time, fast streams and slow streams.
So that's what we're seeing here, this sort of orange stuff.
The background stuff is the solar wind. And from time to time, you get these explosions almost. You get these huge amounts of plasma and magnetic field ejected from the sun. These are the solar storms. These are the coronal mass ejections.
They're beautiful, aren't they, when you look at them like this?
They're very, very impressive and very intricate.
So here's another view from STEREO of a different storm. What can we see here?
This is a great image because it shows the view through 3 different stereo cameras. So we have the sun, that tiny orange spot there.
Yep.
And then we have one field of view, and then we have the heliospheric images, these special cameras that can image the faint solar wind
So
here.
you see just these are background stars in here with the solar wind in front of them.
And there is Earth.
So we go all the way from the
so
sun.
We go all the way from the sun to the Earth. And if you look, you can actually follow a storm from the sun. There's one.
Yeah, there it
and
goes.
you can see all the ripples.
You can see immediately from this, the shape of the storm is pretty complicated, and this is where Solar Stormwatch comes in, a project you've been involved in for many years. What is Solar Stormwatch?
Solar Stormwatch is a project that asks volunteers to sift through thousands of stereo images. And we're looking at the complexity of the storms. So this is a solar storm. This is a big storm. It looks like there might be another little storm up there, but this is the main one.
Yeah.
And our job as volunteers is to draw around these fronts so that you can see how the shape changes when they move and how fast they move. And that just might have some bearing on how it impacts Earth.
So why in a world in which we've got machine learning and all of this digital technology, why do we need people to look at these images?
Well, computers are very good at sifting through some images, but they're not very good at pointing out the faint and the tenuous and the delicate features that are in these solar storm fronts. But people are very good. And that's what we're doing with Solar Stormwatch. So the more volunteers we have, the more storm fronts we can analyse, and hopefully we can find a better way of predicting when solar storms will impact Earth.
And you don't need to be an expert on the sun to take part.
You don't need to be an expert, you don't need to have had any other training than is on the website. So come and do the tutorial and join in.
Well, I hope you get plenty more volunteers as a result of this. Thank you very much.
Let's hope so. Thanks.
Whilst the scientists get their images from a NASA spacecraft to view activity on the sun, down here on the Earth's surface it's also possible to see what's going on. Pete Lawrence spent a day in the sunshine down on Thorney Island on the south coast to tell us how.
You'd think that observing and photographing the sun would be a lot easier than observing and photographing the night sky. But of course you still need the clouds to keep out of the way, and as ever you need to be really careful and not look directly at the sun. By far the safest and most common way to observe the sun is by using a white light filter over the full aperture of the telescope. Now you can buy sheets of specialist white light solar filter and you make your own filter to the size of your telescope. But before you put it on, there are a couple of things you need to make a note of. First of all, the telescope obviously mustn't be pointing at the sun, and you need to check that the filter hasn't got any rips or holes in it. And to do that, you just hold it up to the sun and make sure that it's actually intact. Once that's done, slip it over the end of the telescope and you're good to go. The wonderful thing about observing the sun is that you're never quite sure what you're going to get on a day-to-day basis. Today, there's not a lot happening on the sun's disk. In fact, it's almost totally blank. But what would you expect to see using a white light filter? Well, what you're looking at is the photosphere, the visible surface of the sun. And that has a granular texture. It's a bit like rice paper. It is actually called solar granulation. But as you look over the disk of the sun, you notice that the central bit is bright and the bit at the edge is dimmer, and that's called limb darkening. Sunspots, if they're there, look like dark patches. They're cooler regions on the sun's surface. Sometimes they grow into large features which are much larger than the planet Earth. And if that's tickled your astronomical fancy, then you may want to start using a speciality filter, something which seems to have attracted the attention of the local cows. Now, by far the most common type of speciality filter is called a hydrogen alpha filter, and that literally allows you to see the sun in a new light. Now, when I look at it on the computer screen here, what you see are lots and lots of swirling patterns which are formed by hydrogen plasma following the magnetic field lines above the sun's surface. Also, on the edge of the sun, you see clouds of hydrogen lifted off, and these are known as prominences. If you're really lucky, you'll catch an active prominence, and that will change over a time scale, maybe just a few minutes long. You can also see bright patches, which are flares. Now, hydrogen alpha filters are great for taking images through. And if you do manage to get any H-alpha images, don't forget to put them up on our Twitter and Flickr feeds. And finally, when you've finished observing and imaging, don't forget to turn your telescope away from the sun before you take your filter off. Otherwise, you may damage your telescope or your camera.
As our modern world becomes more dependent on satellites and technology, the need to understand coronal mass ejections becomes more pressing. That's why 2 new satellites are being planned. Solar expert Lucy Green has been finding out more about these missions.
There's a temptation to think that we understand our sun. After all, we've been studying it in detail for hundreds of years. But along with coronal mass ejections, we still need to learn more about the origins of the solar wind and the solar dynamo.
The solar dynamo is created by the movement of the sun's fluid interior, and it's the cause of the magnetic field lines that create solar storms. But it's not completely understood.
And that's been the motivation for 2 new solar probes, and both plan to go closer to the sun than ever before.
Barring mishaps, NASA's Parker Solar Probe was due to be launched yesterday, and its destination will be close enough to the sun's surface to fly through the source of the highest energy solar particles.
The Parker Solar Probe is a mission of exploration to measure the gas and the magnetic field close to the sun, to understand why this material is expanding out into the solar system. And hot on its heels is this, ESA's solar orbiter, and it's being built here in Stevenage. It's hoped that Solar Orbiter will discover the connection between sunspots, flares and coronal mass ejections on the surface of the sun and the solar wind.
Michelle Sprake is one of the mission engineers tasked with making sure it survives when it gets there.
Michelle, we're lucky enough to be in front of the spacecraft now. What stage of the build are you at the moment?
Okay, so last week we achieved a major milestone on the project. We assembled all the individual panels that make up the spacecraft and attached them onto the core structure for the final time. Now the activities over the next few weeks are going to be checking all the alignment of the instruments to attach the external instruments that aren't already on the spacecraft and carry out a lot of thermal testing to make sure that it can withstand the environment that it's going to see close to the sun.
Just how close to the sun will Solar Orbiter get?
So Solar Orbiter will be about 0.28 AU, which is just inside the orbit of Mercury or just over 40 million kilometres away from the sun. It's going to get very, very hot, maybe twice the temperature of your average oven at home. Obviously our heat shield is integral to keeping the rest of the spacecraft cool. So we need a very intelligent attitude control system to make sure that no matter what happens, even in a failure case, the sun is behind the heat shield for the rest of the spacecraft.
And I've always wondered, so Solar Orbiter will be heated up to about 500 degrees on the sun-facing side, but how hot will the instruments inside the spacecraft get? Will they be operating at room temperature? Is that the kind of difference we're talking about?
Yeah, it's sort of 50-60 degrees. The heat shield really does just help us to keep those electronics and cameras on board within a region they can tolerate.
And it's not just about temperature, is it? I mean, the spacecraft will be bombarded by particle radiation from the sun. How do you design it to be able to withstand those conditions?
Okay, so the spacecraft has been designed to be radiation tolerant to a certain level. The chances of a coronal mass ejection hitting the Solar Orbiter spacecraft are probably quite low, but we do have that radiation hardening in place.
How many instruments are there, and is it a particularly complex mission?
Yes, it is. We've got 10 instrument suites on board, but within there's just under 20 sensors to take account for and fitting them inside the spacecraft.
And it's not that large, is it? That's quite remarkable to think of that number of instruments inside.
Yeah, it's very tightly packed in there with all these scientific instruments, which is good because to work out how the sun operates, you need to have a good quantity of instruments on board, and they all complement each other and look at different parts.
Well, Michelle, thank you very much. It's been really good to get an update on Solar Orbiter, and good luck for the final few months as we run up to the launch.
Thank you very much.
The success of Solar Orbiter will be critical to our understanding of the sun's activity.
We think the sun's magnetic field is generated in a similar way to the Earth's, but it's much more dynamic and variable. We have an 11-year sunspot cycle, over which time the magnetic fields of the sun migrate up towards the poles, and the polarity reverses over this time. On top of that, the magnetic field extends out into the solar system, flowing over all of the planets. And Solar Orbiter, for the first time, will measure these magnetic fields, but also give us the possibility to see the magnetic fields as they migrate to the poles of the sun.
To do this, Solar Orbiter will image the sun's atmosphere and measure the density, speed, and temperature of the particles heading across the void. But one of the most critical and possibly most sensitive instruments will be the magnetometer, designed to measure the minute magnetic fields in space carried by the solar wind. At Imperial College, I met Tim Horbury, who's the principal investigator for this piece of kit.
Tim, you're responsible for the magnetometer on board. Why is that instrument so important?
Well, the sun's magnetic field drives all of its dynamics. So there's a lot of energy stored in that magnetic field, and when that energy is released, for example, into solar flares, it accelerates particles and releases particles throughout the solar system. And the magnetic field, as it flows away from the sun, it controls where the particles go. It's really the highway by which particles travel from the sun to the Earth. By measuring that at the spacecraft, we can see the connections between the spacecraft and the sun itself. The big thing is to watch it as it evolves. So when it's close to the sun, you think of it like a candle. If you snuff out a candle, very close, you see little fine wisps of smoke. As it goes further away, it sort of diffuses out. By the time it's got to the Earth, that diffusion process has happened, so it's really hard to make the connection between what we see and what's really happening on the sun.
I think magnetic fields can be quite an abstract concept. So what does your instrument that measures these fields look like?
So it's quite nondescript. There's a little black box that lives inside the spacecraft where the various electronics gubbins lives. And then we have these two sensors, and they actually live on a boom far away from the spacecraft body because the spacecraft itself makes magnetic fields that are bigger than what we want to measure. So we spend a lot of time trying to reduce those magnetic fields, and we finally build these very high-resolution sensors.
So this is the magnetometer,
That's exactly right, this sensor, that's right. So it weighs a couple of 100 grams, lives a few meters away from the spacecraft, and it's basically got a set of coils inside it, which are very carefully wound, and you can see the very intricate wiring that's involved here to connect this up to the spacecraft body itself. And this measures magnetic fields that are incredibly small, far smaller than we see on the Earth. So this instrument itself is sensitive enough, for example, to measure an MRI machine operating across London.
That's incredible. And what do you hope to discover with Solar Orbiter? What questions do you want the mission to answer, and what do you really hope that your instrument's going to find out?
What we really want to do is understand how the sun makes the solar wind. We can see it at large scale, but this fine scale detail, we know there's a huge amount of little magnetic energy releases happening on the sun all the time, but we've never been able to resolve them in detail and never see what they look like in the solar wind. But really, I'm looking forward to discovering something that we have no idea about. You don't explore somewhere new without discovering something completely new, and I think that's what we're going to do with Solar Orbiter. It's going to be so exciting.
Solar Orbiter is due to be launched in February 2020 from Cape Canaveral, and after completing a 3.5-year journey, it will give us our closest ever view of the sun.
The sun is ever present in our lives. It gives us light, warmth, and even life itself. For Richard Carrington, the first observer to record a coronal mass ejection, it was just an unusual occurrence. But we now know that these are capable of severely damaging the world we live in today. Hopefully, with new satellites and new observations, we'll be able to get a better understanding of these activities and predict future coronal mass ejection events. Good night.
And if you feel the need for some scientific irreverence, join Brian Cox and Robin Ince with the Infinite Monkey Cage on BBC iPlayer Radio. Behind the scenes at NASA, will this expedition to Mars finally be successful? The stakes are high, and it's not a simple thing to organise, as we find out next.